Morning. So it's the night after the party, right? Amazed to see so many people sitting here. So I was out last night with people at like 2 o'clock in the morning, and I said, I've got to do my keynote first thing in the morning, but you guys can watch the live stream, right? So there are people sitting in bed right now watching the live stream. Oh. Anyway, so topic today, I want to talk to you about code deletion. And this is a funny thing because, I don't know, how many people here like to delete code? Yeah, so it's like everybody's hand goes up. And this is a very funny thing about this because for all of us within the industry, it's like we know that we're basically sitting in code bases that look chaotic and crazy. We have too many things. It's almost like having in a house, an apartment, a garage that has too many things. And the thing is, we all want to delete code, but we hardly ever do it, right? And I think that what's funny is that we haven't developed enough practice now in the industry about how to do this sort of thing, how to go and actually systematically try to go and figure out which areas of code are worth keeping, right? And which areas of code are worth going and getting rid of. So this talk is really an attempt at going and digging into this particular thing and helping us understand a bit more about when we can delete code, when we can't delete code. And beyond that, if you are going to delete code, sometimes you have to replace it, you know, with basically some reduced feature set of what you had previously. So I'm going to dig into a bunch of different things, practices around this sort of thing, and take you along for a ride with this. So the big question we have to ask is, when can we delete code? And what's rough about this is that when we look at code, we can't really see more beyond its surface appearance, right? We see the code itself, but we don't really know what's happening with it at runtime. And this is very rough. You know, essentially, you know, we have code coverage, but when you look up code coverage, you know, in Wikipedia or just about any other place, one of the things that you understand or you discover is that when people talk about code coverage, they're really talking about test coverage most of the time, right? So we use code coverage to go and figure out whether certain areas of code have been covered by test. The rough thing about this, though, is that if we were to try to figure out whether certain code is dead or not, what we'd really like to be able to do is have coverage of our production code, right? How many people run coverage in production? Nobody. Nobody's hands went up. Big difference from all of the hands that basically said, oh, you know, I'd love to delete code. But this is the big problem. Coverage tends to be expensive, okay, within a production environment. And we just aren't doing enough of this to go and really understand enough about where areas of code are actually being used in our code base, okay? And this is very rough because, you know, essentially we look at code, we have the assumption when we see it that it's valuable. But we don't really know enough about when it's being used to figure out what its actual value happens to be. So I want to carry you through a bunch of different classifications first before we start getting into practices around deleting code. There's this one here, unreachable code. And I'm sure that most of you are familiar with this, right? Some code basically cannot execute at all inside your code base. And usually this is because of particular conditions that are just impossible to satisfy. And what's nice these days is that in any compiled language, pretty much, there's a lot of work that's been done to go and actually get rid of unreachable code. And the funny thing about this, though, is that quite often we aren't given notification about this. It's like the compiler or the linker, the runtime system goes and discovers that some code is not being used, it's impossible for it to be used, and it just goes and pulls it out from the image or the executable. Which is a little bit of a shame in a way, because what we'd really like to do is basically know this at the source level. If we know that some code can't be executed at all, we're better off just going and removing it and not having to look at it at all. And some languages are very good about this, others not so good. Like Java, for instance. It's like if you basically try to create a path where there's no possible execution, when in some cases, it will tell you that this is impossible and it won't even compile. It will just basically tell you there's an error here. Here's some code which is actually dead and impossible to go and reach. Dead code is kind of funny. I always assume that unreachable code is dead code in a way, but definitions I've seen through Wikipedia and a couple of other places point out that it's really something else. Essentially, dead code is code that actually does execute but does not affect the actual results. And for quite a while I used to use the term zombie code for this because it was kind of like, you know, it's kind of alive in a way because it's exercised. But the fact is it doesn't really affect anything at all. So how do you detect dead code? Yeah, it's kind of funny. Sometimes we spend enough time as developers being aware of what's going on in an application, that we can start to get a sense of whether something is dead or not. But absent having that kind of production coverage information, in many cases we just simply don't know. But there are some other ways to go and figure this out. I'll talk about them in a little while. There's this other term, okay, oxbow code. And it's funny because it's not like a real classification, but I love the fact that it has a funny name, right? But it also goes and indicates something which is quite interesting to us. And I'm sure some of you seeing this definition can recognize places where you have this. Okay, fragments of program code which were once needed but now are never used. Okay? So it's essentially places in the code base where you had something, there was a valid reason for it, and somebody just chose not to delete it. Okay? Now this actually goes in overlaps between dead code and unreachable code in a way, right? Sometimes it's like it's there, it's a function that nobody calls, you know, or basically a particular path that somebody goes and says, well, you know, it's kind of like that's really never going to be exercised, but we're leaving it there for one reason or another. But beyond these things, okay, these different varieties of code which you can just actually get rid of is this one, low value code, okay? And this is not really a term in the industry yet at all. I kind of hope that we sort of push forward and basically make it a term that we all start using. Okay? This is essentially code that's there in the code base, it executes, it produces values, it actually produces value for the users, but maybe it's just not enough. So, as I mentioned earlier, coverage is one way of going and approaching enough information to go and actually take action upon these things. But, you know, it's funny to go and notice that coverage is something that we just basically do in test situations rather than doing, you know, in production. When people do run coverage in production, it's quite often under the guise of profiling. So you have things like gprof, right? You go and get ahead. You know, this gprof will basically instrument an app, you know, code and allow you to go and basically see what's going on at particular points in time. You have dtrace. You have a variety of other schemes. There are various, if you look through the literature on profiling, you find a bunch of different ways of approaching this information about whether things are being used or not. And again, quite often under the guise of profiling. So one thing that's kind of interesting is like the stack-based profilers, where essentially you have like an interrupt firing every once in a while, and what it does is it goes and takes a snapshot of the stack and kind of dumps it someplace. And so interesting paper here, this guy was basically showing a very, you know, low, lightweight technique of going and doing profiling in Python. You snap the stack, you basically go ahead and throw it off someplace, build a histogram of all the stack frames you've saved, and you can start to go and get a sense of where it's spending its time, your application is spending its time. Okay? But there's another thing. There's another way of going and approaching some of this information as well, something called mutation testing. Anybody ever hear about this at all? Yeah, some people have, and that's good. And it's funny, I looked into this because I haven't used this in a long time. There's a guy I know in the industry, his name is Ivan Moore. And he wrote a very cool tool for Java years ago. It's called Jester, okay? And what it would do is it would basically go and take your code and do things like invert conditions or change constants in the code. And then basically it would do that like one at a time and then run all of your tests. And essentially what would happen then is it would go and flag tests that, you know, actually would go and give you an indication that this is a particular thing which isn't being covered by your tests because the tests aren't failing for this particular reason. Now this is slightly different from coverage. You know, essentially when you invert a condition or you change a constant and your tests don't fail, it could mean the code is unreachable or the code has not been covered by the tests, but it could just as well mean that essentially the code has been exercised, but essentially the values it produces are just never really used at all, right? So this gets back to that definition of dead code I was talking about a bit earlier, or zombie code. It executes, but it's inconsequential. It produces no significance. So I think the mutation testing is something which is kind of fascinating, and it's like, I want to kind of like push people to do more of this. It would be interesting to resurrect these projects to see, you know, where they kind of stand right now. It's kind of funny, Jester was the Java mutation tester, but there were a variety of other ones that were named too. Essentially, you've got a nice thing here, J for Jester, so there's one called Pester for Python, right? So then you can have Fester for whatever language you have that has an F in it, right? So yeah, this is a way of going and approaching that information, of going and discovering dead code. There's another thing I've been working on recently too, and it's kind of recognizing that what we'd really like to do is get this kind of information all the time in production, right? The reason people don't run coverage in production is because it takes a while, right? It actually goes in, significantly slows down your programs, particularly coverage that's going to be full coverage, okay, as opposed to the thing where you're going and snapping the stack frame and trying to understand what's going on with it. So this thing I'm calling a feature probe is essentially to go and place statements within your code and essentially set it up so that you just run your code for about a month, for instance. And what this statement does is it goes and logs if it's actually been hit, right? So the tool I'm working on now called Deadly, right, to find dead code. You have a particular marker, it has to have a unique name. And what happens is that essentially it goes and logs someplace, and then periodically, like on a cron job, what it will do is it'll basically go and check to see whether the markers you happen to have in your source code have ever been hit within, say, the past month or something like that, right? So very, very low-tech tool, and the thing is it's cross-language, to go and do this sort of thing. But you can set this up in such a way that it's really, really low overhead, even in a tight loop. Maybe just like it just goes and records, once a day that actually this particular branch has been hit. So you just find places in your code where you suspect that things are dead, right? And then you put these probes in and leave them in for a period of time and then find out really whether you actually, in say a month of production usage, ever hit these things at all. And I'm sure you're hearing this and you're saying, okay, well that's great, but that doesn't prove anything. And it's like, that's true, it doesn't prove something. In many applications you can have paths of code that don't really get executed more than say once a year. But they're still significant, they still have users, and there's no reason why you can actually go ahead and there's no reason to go and actually get rid of them. Okay. So, yeah, but I think we need to kind of do more of this sort of thing to get enough data to go and kind of support us as we're making these choices to delete things. And another aspect of this as well is to go and kind of recognize that at the feature level, okay, when we have some application and we can go and get a sense of all the things that it does, it's nice to go and basically get a sense of how these particular features map to the overall architecture that we have. And this is a thing I do with teams quite often now, is we look through all the use cases, the things that have happened in the past, and we say things like, if we pulled out this feature, what's the impact going to be, right? And there's a bit of analysis that's involved in going and doing that sort of thing. Another thing that's kind of fascinating about this is that when you actually start to go and back this up with production data, and I've done this thing with like very low-tech, approaches, over time you can start to say, wow, it's like we have this particular feature, it's not being run all that often, and you can start doing this very interesting trade-off, right? And I think this is a very important thing for us to do as developers, is to go and start to, if you understand enough about how something is being used, you can say things like, hey, you want this new feature, and it's like, I've gone through the code base, and adding this feature would be pretty easy if this other feature wasn't there, right? Has anybody ever done that at all? Yeah, sometimes we do this in very extreme cases, but I don't think we really have the ethic of this yet. We don't really have that sense that this is an important thing to do. The typical relationship that we often have with business, is that we do what they want, right? We essentially go ahead and we add the features that people want because we are in the business of making software to solve problems. But the thing about this that's very rough is that we don't have a strong sense right now of what the carrying cost of code is. And I believe it really is significant. I know one experience I had very early in my career was to go in and basically take like a distributed lock data structure and optimize it. I had joined a team recently and they wanted me to go and do this work. And I remember looking at the code for a full day, trying to understand it well enough to start the optimization process. And I started to notice that they had this one feature to go and lock multiple nodes at once. And I thought, wow, the optimization would be much, much easier if we didn't have this particular feature. And just as an experiment, I did a search across the code base and discovered it wasn't being used. And I thought, oh, fascinating. So I went to the people who were asking me to do this, and I said, what's happening with this? Why do we have this multi-lock feature? I said, well, we thought it would be useful someday. And I thought, yeah, great, it'll be useful someday. Can we get rid of it now to go and solve our current present problem? And essentially they said yes, and we went and removed it to make things better. But this is a very, very significant thing for us to notice, is that when we look at code, we assume it's being used. And if we are looking at code that isn't being used, we're looking at a lie, right? And this lying is not just a technical thing, it's also a business thing as well. If we have a sense of our portfolio of features in an application, And some of these things are not being used more than, say, 1/100th of a time. If we don't have that information, then we're not able to make effective decisions going forward about what we want our applications to be, what we want our business to be. So yeah, there really is a cost case for going in and doing all this kind of stuff. As well, I guess to kind of like wrap up this portion of this, we have things that we can do when we detect these things, right? Unreachable code, if we're lucky working in a statically typed language, we'll have compilers removing those things for us. You know, you'll get compiler errors, warnings. It's very safe to go and delete that whenever you detect it. If you really have mutation testing in place, you can figure out when you have something which is dead and delete it. Okay, you can do the backward analysis to figure these things out, but it's kind of an iffy case. You really have to have test cases that are exercising things fully in ways that they can be exercised within production. But this other thing, low-value code, you know, essentially this is the odd place. This is the place where you have something which is being used, and you have to go make the case. You know, do we really need this? And if the answer is no, you have to figure out what you're going to do. And in some cases, that is saying to those customers, we're not supporting this anymore, right? Another thing, though, is to also say, well, you know, maybe we are supporting this, and this kind of ties back to something that Greg Young was talking about in his keynote yesterday, going and putting a human in the loop. I'm actually talking more about that later, where we set things up so that, you know, if somebody wants to do this particular thing, then a human has to go and get in and do that thing as opposed to having the software do it. At least to go and sort of migrate people off into an area where things can be better for them and better for the sustained development of the system. So strategy is basically, you know, when you find these things, unreachable and dead code, get rid of them. When you are dealing with like low value code, if you can figure out what your mitigating business action is for those things, what you want to try to do as much as possible is disable it at the entry points. You know, through, you know, flow graph analysis, figure out where you are actually going to initiate calls to these particular areas and try to cover it at the top as much as possible. And this really does make it a business case. You have to go and sort of figure out that, you know, at the point at which you receive inputs into the systems, you are not receiving this intent anymore. And then you have to go through the process of figuring out, now that you've sort of like kept these inputs from coming into the system, now is this particular area of code unreachable? And if it is unreachable, then you can start to remove it. Okay. Let's get into rewriting now. Okay. Once we've decided we want to get rid of some code, to me the ideal case is to have less code. You know, I just really, you know, if we can have less code to do the same amount of functionality, great. If we can have less code even with reduced functionality, that's great as long as we produce enough business value to keep the business, you know, healthy. It's kind of an interesting thing. It's good to try to do more with less because you have more options in the future. But sometimes you have a very complicated piece of code, and what you want to do is you want to rewrite it. And you're going to have to go through a process of deleting code to do this. It's interesting to notice that most of the rewrites that people do in the industry these days are really motivated by technology and architectural change, right? It's very, very rare that somebody's working a particular technology on a platform and they choose to go and rewrite the application using exactly the same technology. And a lot of this has to do with the cost of going and doing this particular thing. They think, well, you know, things are already very cruddy. We're at least going to go and try to change platform also. We're going to do this kind of thing because, you know, we're already incurring this much expense. We might as well go all the way with these things. And quite often it's easier to sell the business case as like, hey, we're moving to this fresh, shiny new platform, as opposed to just the case of like, here's something which is just so cruddy it's hard for us to maintain, we need to rewrite it. But the thing about this, though, to notice as well, is that big rewrite projects tend to be very problematic. And we've known this for quite a while within the industry. So, you know, the go-to pattern for this is the strangler application pattern. And I'm not really going to get into it in a great deal of depth. But this is something that's been written up a number of times in blogs. I encourage you to go and read more about it. The idea behind this is essentially that you have an application. There's an area of code you want to rewrite, and what you do is you take the inputs, kind of as events, and divert them to a new piece of code that you're building. And sort of like, over time, kind of strangle the old code in the sense that it is getting less and less events coming into it. So you try to go and start out with like the good cases in the beginning, kind of like divert those good cases over, and progressively move towards going and dealing with the edge cases. And eventually you get to the point where you can go and get rid of the old code entirely. So it's kind of like building a new path and then going and getting rid of the old one. The toughest thing I've seen with the Strangler application pattern is people starting this and not quite finishing it. Because, essentially it is a process of exploration as you're doing this work. You're going and building something side by side with what you've got, and you start to get into all these crazy edge cases. So I think the thing that's most important with this is to go and really have the desire to go and carry it through to completion. Otherwise, you just live with an excessive amount of complexity for a long period of time in the code base, and we just don't really need more of that, really. When it comes to going and figuring out how to rewrite, what to rewrite, the key actions are this. You have a particular area of code, can you find all the inputs and outputs? And what's funny about this is that sometimes we have inputs and outputs that we aren't even really aware of unless we dig down into the code. An area of code that might have a silent output that you're not aware of is something which goes and accesses some global variable or changes state in a global mutable variable. And looking at the code at first glance, you don't really see this, and you don't really see that this is really an output of your system. So mapping the inputs and the outputs is a very important thing to go and figure out what the scope is at which you're going to go and remove things. The other thing I ask, which is something I haven't really seen people talk about all that much, is when we are rewriting something, will we basically make an effort to reduce conditionality? Okay? And what I mean by this is getting rid of edge cases as much as possible. This is really something I'm spending a lot of time on these days, is recognizing that edge cases increase complexity. They often make our code less clear, and if we can get rid of them, we often end up with something which is simpler and more robust at the same time. The other thing, too, is can we take the piece that we want to rewrite and scope it for characterization testing? Anybody know what characterization testing is? Some people do? Okay, I wrote about this in the legacy code book I wrote years ago. It's really an approach to going and writing tests for code that exists already. We'll have an example in a little while. The other thing, too, is can we basically run redundant? And this is an interesting pattern. We'll talk more about this later, which it's if you are going and building out something which is going to replace something else, and you have identified all the inputs and outputs, essentially made it almost like a pure function in a way, a pure functional area, can you just sort of run both of them, right, in parallel, and in production, right, and find out whether there's any differences at all. If there are differences, you revert to the values produced by the old code and log the fact that there was a difference. And you keep doing this until you really have assurance that you really are replacing the older code. This is really an old technique. I first saw it written up, I think it was actually used in Excel at Microsoft, written up by a guy named Steve McConnell ages ago, or Steve McGuire, I forget which one. But it's a very handy thing. If you can afford to run a computation twice, do this as often as you can to make sure that you really have it right in the replacement. So, let's skip that. Characterization testing. What this is going and saying, I want to write tests that aren't about proving correctness. They're about characterizing the behavior that we have right now in an application. And I want to show you a bit of this because it's really, if you're used to doing TDD, it's kind of like a bit of an opposite of TDD, but it helps you when you want to go and get enough tests in place to refactor your code or rewrite it. Look at this piece of code here. Is this not the most beautiful piece of code you've ever seen? It's beautiful, right? How come nobody's smiling, right? Yeah, no, it's kind of crazy, ugly code. You can see it's going and doing some conditional work based upon open angle brackets and closed angle brackets. It does some formatting around almost like markup style behavior. But if you're like me, you look at this and you're kind of like, what the hell is going on with this? How does this thing even work, right? So the thing I like to see testing as, when you're dealing with existing code, I see testing as a way of answering questions. You get curious about something and you write a test that asks what something is doing. So let's go and try that out. Here I write a test. I'm saying, okay, let's go and do something very simple. I want to see if this code formats plain text in a way that it goes and just returns it back without modification if there's no angle brackets in it. Because that's a good guess at what this stuff is doing. So I write this little test, and I basically see that when I put in just some plain text with no angle brackets, it goes and returns the plain text with no angle brackets, right? So, yay, I've got a passing test, right? And it shows what the behavior is. If I have enough of these, I can refactor or rewrite. This is too much too soon. Okay, here's how you really approach characterization testing. You approach it like this. Okay, what's that X for? See how X is the name of my method there? Well, the X is because I don't know what my test is going to do yet, right? So as I mentioned earlier, what we're doing is we're asking questions. So what I'm going to do is I'm going to ask an extremely simple question first. Can I pass an empty string in and have it produce an empty string? And I really like to start with these basis cases. Quite often they're edge cases. And sort of see what happens at the edges within a particular piece of code. This is almost like anybody who's done like proofs in mathematics. It's like mathematical induction. Start with the basis case and then move on from there. So let's see. I make the assumption that that's going to produce what it does. And sure enough, it does that. So I can say formats empty string as empty string. Now I have a name for it because I understand what's going on with it. I understand what it does. Now, the thing about this that's kind of funny is that, let me go back here for a second. I put an empty string there, and it was just lucky that that empty string was the actual value that was going to be produced. I could have put something else there, and what would be funny about this is that essentially I'm asking the question, if I do a format text on an empty string, what happens? And if there was a failure, guess what would happen? I get the test failure, but I'd also go and have it tell me what the actual value is. When you're characterization testing, what you do is you take the actual value and you plug it into the test. And it feels like cheating, right? Because essentially you're saying, oh wow, I'm taking the actual value and plugging it in. But our goal is not to find bugs, our goal is to document existing behavior. And this is the nice thing about characterization testing, is it is so easy to do, right? Once you're able to break dependencies enough to go and start to write tests, you just ask questions. And then you find out what the answer is. It's like, oh, surprise. This is a little bit different than what I thought it was. Plug it in as the expected value. Your test passes. Move on to the next one. And you do this over and over and over again until you kind of feel that you've answered enough questions to be able to go and do the rewrite that you want to do or do the refactoring that you want to do. So you can also ask questions like this one. If I pass null into format text, what gets produced? Right? Is that a good question to ask? Yeah. Okay, so we can go and ask that question. And, of course, you discover then that essentially what's going on is it's going to, throw an exception. And we're doing too much there. We can get rid of the assertion entirely. Just run format text on null and see that it throws a null pointer exception. I feel weird about this test. The reason I feel weird about it is I'm not sure I want to document this, right? I mean, how many of your methods check for null arguments? It's kind of interesting. I just like to think that in the sane code base, we don't have to do this because nobody actually passes null, right? And this is like a baseline of sanity you can see in many systems. There should be almost like an implicit rule that people don't pass null, and if that's the case, then you just have to go and check for null in the places where it can occur and make sure you're never passing on to anybody, which means that you have, this sense of like a safe area in your code where you don't have to check for null, right? Because the alternative is madness, and believe me, I've seen madness, right? Scattered null checks all through a code base, and if you look back and try to figure out why they occur, typically it's because, oh, we found a null pointer exception. Let's put an if condition there to make sure that doesn't happen again, without going back to the root cause of it. But yeah, null is really a problematic thing in most of programming. We should try to go and avoid its spread through systems as much as possible. The bigger thing with this, though, is to notice that when you write tests like this, characterization tests, one thing you will discover is you will discover bugs at times, right? And if you discover a bug, you have to go and ask yourself, well, is that really a bug, right? Common thing that occurs, you'll start asking a question about a particular function you're working on, and you'll discover some case where it's obvious that you have a bug. And then you ask yourself, why has this never occurred in production? And then you look and you realize that basically the caller of the code is never going and producing values that would cause the bug to be, uncovered. And so then you have that big question to ask yourself, do I fix this or not? And there's no solid answer on this particular thing. It comes down to where you want to have particular barriers in your application against particular things. I think also a big aspect of this is noticing where you have code that has only one caller and code that has many callers. When you have many callers, you have to be a bit more defensive, I think, or a bit more explicit about what you're accepting than in other places where it's just a single one and the caller is kind of guarding you from particular conditions. So yeah, we may not have that as a test in our system. So let's see. So this code again. Okay, we can look at something like this. Here's something where we just go and pass in, angle brackets, and it goes in and just removes them entirely. And this may be something that you look at and you say, that's kind of funny. Would I ever want to see that in a document that's being formatted? And you have to decide whether that's really a bug or not, right? Maybe it is a bug, maybe it's not, depending upon the context. Okay, so to kind of like go over what's going on with characterization testing here, these are the rules I kind of use with this. Start with X. You don't know what your test is going to be named in the beginning because you don't know what the test is going to do. Okay? It's great to use expressive long names when you're writing characterization tests because you're documenting what the behavior happens to be. A very common pattern I have with this is I'll start writing 3 or 4 tests. I'll use one naming scheme, and then I'll go back and I'll revisit the naming scheme and replace it with something else because I discover a better way of describing the behavior that I'm characterizing, which is this, renaming to tell a story. And then the other thing is making the call on bugs. Like there are certain things which will be considered bugs or not. You have to decide what they're going to be and decide when to approach these things, when to bolster your code. And the last thing really is be curious. Okay, the entire process is driven by being curious about what the code actually does. And if you are curious, then writing the test is easy. Okay? So there's another aspect of this too, which is interesting, is you want to ask ourselves, I mentioned here, what was the goal? I think this is very important when you're talking to people about writing tests for existing code. I didn't say there was any particular goal at all when we were characterizing behavior for this. But the thing is, you can spend a lot of time. We could probably end up writing about 10, 15 tests for this small function. And we have to ask ourselves, is that really time that's worth it? So what is the goal? Well, in some cases, you want to refactor something. And then what you should be doing is you should be looking at the particular area that you want to refactor inside the code and asking yourself, how do I basically prove that the refactoring I'm about to do isn't changing behavior? And then you write tests to kind of like target that particular spot in code. Another thing is you may be choosing to rewrite something and you have a good idea of what it does, but you want to go and sort of like bolster your understanding about how something works. And so going and writing with that particular intention is valuable also. So to give an example of this, here we have an example of a method called charge, this class called residential account. You pass in gallons and a reading date, and it has this business logic there. And suppose, looking at this code, that we want to do a refactoring. We want to basically take this piece of code and we want to extract it out. Okay? What can possibly go wrong when we extract this? It's kind of funny to think about, right? Essentially, when we extract this, we're going to have gallons being passed in as an argument, right? And if we're staying on the same class, we don't have to, balance is not going to go across any boundary that we have in the method that we're extracting. So to me, it's perfectly reasonable to go and say that we will check balance, we'll check gallons, but since residential min and residential base are part of the class as constants, we probably don't have to write any tests to make sure that those things, are being used effectively. We can just basically go and test based upon these particular things. You have to go and look and see what could possibly become part of a new interface you're producing through refactoring, and use those things as the particular points you're going to be testing. A thing which is kind of funny about this is if we're trying to write these tests to understand how things work, we have lots of unit testing frameworks in the industry. There are some techniques you can use that kind of help you out with some of these things. This is one which is very, very counterintuitive. I wrote about it years ago, but not too many people have run across it. I enjoyed talking about it because it's so useful. Imagine you have a giant, giant method, and you want to go and write some tests against it, but you can't really refactor it very easily in the beginning because you don't know enough about how it works. One thing you can do is this. You can essentially go ahead and introduce a new public variable inside your class and assign to that variable in the context of the code that you're about to refactor. If our idea is that we want to go and just refactor by extracting out some of this stuff here, we might be interested to see that balance has the same value after this computation when we refactored it. And so what we do is we assign to that, and then we can go ahead and write a test that's going to go and check that. Now, it's kind of funny about this. Does this seem kind of weird? You're adding a public variable to a class in order to go and write a test to understand how it's working. Is anybody else feeling like this crazy shaking feeling now that this is the most insane thing they've ever seen? Yeah? Well, here's the thing which is interesting about this. as developers, whenever we change code, we have the default assumption that we're basically making it for a production reason. But this is a case where we can change the code temporarily in order to get some information. And then before we check our code in, we just get rid of that variable, and we get rid of the test that we had there. So the idea is we can alter our code a bit to understand more about how it works. And then once we've done the refactorings, get rid of those tests, because we don't really need them anymore. We've used them just to prove the refactoring to ourselves. Get rid of those variables, and then check in the result. Okay? So it seems like cheating, again, but it's not. This is a way of going and approaching some bigger refactorings. It's nice. This is the kind of thing that would be kind of nice to have some tooling around. There's a tool I wrote a while back. I haven't really put up. It's called Vice. It allows you to sort of like record values at particular points in the execution of your code. So imagine you have test cases around this particular method charge, but they don't really have assertions in them. What happens is they do exercise a lot of the functionality in the method. With this tool called Vice, what I would do with this is the very first time that it's executed, what it does is it takes the value of balance and it saves it to a file. And the very next time that it's executed, it goes and takes the value from the file and compares it against the value that was there previously. Okay? And you just basically save a stream of values and you check to see the stream of values is the same the next time the tests are run, which is okay in single-threaded code. But this allows you to sort of like put in these kind of ways of pinning down behavior in a particular, under a particular set of tests that's rather deeply embedded and not easily accessible through the interfaces of the classes and the methods. I'd really like to see this sort of thing become part of IDEs. I think it'd be kind of a nice technique. So reducing conditionality. This is the call graph for Apache web server, back in the day. This is not up to date. This is Microsoft IIS. Which one do you want to work in? Right? So I'm not going to have to make the case to you that basically conditional code is bad. Am I? Right? Yeah. Well, I'm going to make it anyway. If statements. Okay? It's funny now, in the industry, we're getting closer and closer to a bit of an ideal with this. Loops are kind of problematic, and we've been moving away from loops quite often. So we have recursion, we have essentially things like map, reduce, select, filter, all these operations which occur like in various libraries to prevent us from having to go and write explicit loops much anymore. Same thing can happen with conditions. I think the problem with loops and conditions in general in programming is that we have all this empty space here inside of the condition. And it's easy for us to go and say, well, yeah, this is another thing which happens under that condition also. Let's just drop the code inside there. And that's kind of harder to do when you kind of compose operations together going and using these constructs like map and all these other things. Essentially, you end up having to go and basically make a very big block for, say, a mapping operation to go and start to approach the same kind of madness that you have in big if conditions, or big loops inside of traditional programs. I'm not going to get into what this code does deeply, but the thing that's kind of interesting is it does something rather significant, and it really uses no conditions and no loops at all, right? And this is a game I've been playing with myself for a while now. Can I take any problem I'm given and write the code without conditions and without loops? Now, you might look at this and say, well, yeah, sure, there are some conditional things that happen in there. They're just not explicit. I guess I'll briefly explain what this does. This takes a file of numbers, right? And it's kind of like anybody that plays guitar, you kind of know that there are the frets on the guitar and there are the strings. It takes a file of numbers, and there's two numbers on every line. One is a string number and the other is a fret number. And what it does is it produces a musical notation called tablature, where it goes and has like a line for each one of the strings and puts a number on the string for a particular fret when you're supposed to play a melody. And this is something which you can write with loops, you can write with conditions, but by going and using a bit of arithmetic here, okay, I was able to go and produce, in Ruby you can have like you have that thing there, you have like 3 dashes inside of that array. We're saying that times string minus 1. So we're basically taking that 3-dash thing, we're taking that array and expanding it out with copies of itself, string minus 1 times. The net effect when you do this, and you can prove this mathematically, is that you are going to have an array with 6 elements when you produce this, okay? 6 different positions on a string. And that's because string count is 6 and because of the way we're doing our math here. And we don't have to have any explicit conditions to do this. Now, is this code easy to understand? No. And you know why? I'm just not used to it yet. Seriously. I think that's one thing that we often don't quite get about programming, is the things that we think are natural and good and stuff like that. It's because we're used to them, right? But I think there really are legitimate benefits to going and getting rid of conditionality in code. So I'm calling this edge-free programming, removing the edges in code in order to go and make things more like the normal case. Some code I've been working on recently, without getting into details too deeply, you know. Again, no real conditions inside of it, there isn't one loop to go and render things out. This particular function up here, partition, this is Ruby code. What I'm doing there is essentially using this thing to get rid of a condition entirely. I have a list of things, and partition is given a predicate. We ask whether the second field inside each of the list items happens to be a parsable date. If it's a parsable date, that element goes into one list. If it's not, it goes into another list. So this entire expression goes and returns back essentially two lists. So we have like multiple assignments there, valid entries, comma, invalid entries, this big expression, and we run partition on it. So rather than having an if condition, we essentially are able to go and sort of like separate the two cases for this and end up with two different lists. And you might say, gee, this is just cosmetic, but it's like, you know, again, you reduce the possibility of having tangled dependencies because you don't have that big block of code that you can have things that you just stuff in. And it's not just you. People you work with will stuff things into big blocks. This happens all the time in many teams. Okay? And so the last thing I wanted to go and talk about with regard to going and dealing with these things is a strategy I call redundant till replace. Redundant meaning redundant. And I mentioned this a little bit earlier. It's essentially just that technique of when you have a piece of code you're trying to replace and you feel like you've got it pretty much going, try running that code at the same time as the other piece and have a runtime check at the end of the computation. And essentially, if there's a difference between the new version and the old version, always go for the old version, right? And essentially, if they are the same, then you can return either one. It doesn't matter, right? But do this in production often enough to go and really start to go and get the feeling that you have covered everything it takes to replace one case with the other. Okay? And people don't talk about this very often. I think half of it for us in the industry is that we see this as a performance issue. It's like, when do we actually want to go and run things redundantly just to go and make sure that our replacements are working properly? Nice thing is that most apps these days, you can do this sort of thing just in like a very A/B manner. Have selective clients that you sort of like say, look, 1 out of every 10 calls, we're going to go and run this redundantly and see what happens with it. And then, like everything else that we have, if we're gathering enough data, we can take that data and basically use it as a way of moving forward and making an assessment about when we've actually made a complete replacement of something. So, conclusion with this. I think that this is really like almost the next frontier, deleting code. And that's good because everybody loves to do it, right? All the hands went up. The thing about this, though, that's tough is making the business case for it. And I think this is where we really have work to do in the industry, is helping teams, helping organizations understand that there is a carrying cost to code. When it gets in our way, it makes their features take longer to do. And we just don't have that information, right, in many places in the industry now. And that's kind of sad, all right? Anybody here have technical debt? Only 2 people? Okay, all right, good, okay, yeah. I asked the question, please answer, right? So yeah, many hands went up when I asked if they have any technical debt. I really have this theory now that a lot of technical debt that we see within the industry is really a side effect of process. And it's a side effect of split between business and technology in many organizations. In the sense that you have business who wants something, and the technologists basically say, yes, we can do this. And what happens is that the business side of the organization never sees what the run-on effect is of asking for things and having them done quickly, right? We're asking for things and not really sort of like taking, all the mitigating action it takes to go and actually do it well. And when you're in a situation like that, then it's like we shouldn't be surprised at all when we end up having a mess, because we're just talking about the features that we want, and there's just nothing else that's being discussed. So working with teams now, I'm very conscious of this, and I try to say that, look, when you are meeting with business and the people who are commissioning requirements and stuff like this, they need a simple view of the architecture. Okay, they may not be software developers, but make them an architectural diagram, right? This is an architectural diagram. It doesn't look like most of your architectural diagrams. Why? Because it doesn't have any lines. But for this, the lines don't matter, right? The key thing for people to get in an organization is that the features that you want to do impact different areas of code. And then what you need to do is look at this and say, look, as a basis of conversation, if we want the feature restock perishable schedule, right, we can say which particular areas of code are impacted by this. And we can also articulate what the readiness is in that area of code to receive that feature. What's the general health rate for this particular thing? And the thing is, the more often you have this conversation within your teams and across your business, the more that it becomes apparent that certain feature selections at certain times have impacts, right? Certain ways of going and pushing features have impacts, all these different things. And it no longer becomes a matter of like, how quick can you do something? It's really kind of like, how do we maintain the longevity of this asset that we have? And you know, it's funny because quite often now we're used to thinking of code as a bad thing. I'm trying to get you to delete it, right? But the thing is, the code that we have that produces value is an asset for us. And it can either degrade over time or not. And so we have to go and figure out how to go and make sure that everybody understands that, that it is impacted. And I don't care who you are in an organization. You're an accountant, you're a salesperson, whatever. You can understand that, and you should. Because the code that you have in a system is often the lifeblood of an organization. And when people say 2 years from now that I want this particular feature, and the technologists say, no, you can't have this because it's going to take too long. It's like, you know, everybody screams about this, but that's because nobody's been articulating what the status is of the assets. So I think this is really where things need to go. And I think as well, when you have this vision, you can start to go and ask questions like, you know, if we did remove this feature, what gets impacted by this? If you look at the usage data, you can say, yeah, can we do this? Yeah, we can do this. What do we get for that sort of thing? Oh, it's going to be easier to add these other features. And just make it like a full portfolio, but a portfolio of assets rather than a portfolio of features. So anyway, that's what I wanted to talk to you guys about. And I guess I can open up the floor to any questions anybody has. Is that good? Thanks. So, any questions or thoughts? Somebody in the back there.
Thanks. You are recommending reducing conditionality by starting to use functional stuff. Generally, this is not a greatest solution. Yeah. So on one side, like, I don't know, 10% of developers are ready to start doing these things. Mm-hmm. Even less are understanding how to build it. But as a result, internally, there is still same ifs, same for eaches. If you are addicted to, you can read functional code and it will be simpler for you rather than everything else. Yes, that's true. But just as a general solution, I would not recommend it at all.
Okay, well,
because you will ruin your own project and your own team.
Yeah, we know. So it's because I have this gray hair, I can answer this question very well. When I first joined the industry, object orientation was very new, and people were saying, object orientation is too hard for people. We can't do it. We can't do it. There's no way object orientation is going to catch on across the industry because the average programmer can't do this. No, man, we're better than that. We really are. And it's like you have a fear about this, and I understand that. But the fact of the matter is we do forget consistently how much we have learned in order to go and practice the level of programming that we practice right now. And I don't think that we should really hold people to, we shouldn't look at people and think that they can't do it because history shows that we can, you know. And so maybe there's an issue on your particular team and stuff like this, but I don't think that we really are able to move forward until we actually say, we can do a little bit of this. And for some of the examples I was showing there, you know, it's like I was using Ruby enumerable. You have Link in .NET, you have reactive extensions, you also have like Java Streams library now. You can use these in small pieces to the point where people can become used to these things. And you know what? You may be surprised. So I feel kind of awkward. Like
little by little. Yeah, that's my point. Yeah. So same thing for 2 years, run 2 projects from Java 7 to Airbus Java based on lambdas.
Yeah.
And very small steps, because if you write hard functional code, nobody really understands it even 2 years.
Yeah, although 2 years, maybe more people will, right?
Yeah.
So the thing is, you have to take it slow, and that's fine, and you have to figure out what's appropriate in your culture, in your company, in your environment. But I really feel this is inevitable, and I'm sorry to say it that way, but it's like, you know, the work that we have to do is never becoming less complex, so we need higher level tools to do things. And the functional tools are a way of approaching this. The other thing I want to add on to this, though, is that removing conditionality is not just about functional also. Even though I didn't have an example here, an observation people have made many years ago is that polymorphism removes explicit conditionals as well. So in cases where you're able to go and introduce, say, a class hierarchy, you are making a selection through your class choice, which removes conditionality in the code as well. So that's another approach as well.
Any more?
First of all, thanks for a great speech. It was quite interesting. And I was wondering how to apply all I heard here to the project I'm working in right now. And for me, maybe the answer will be you're unlucky and you cannot apply because you have a very exceptional project.
Yeah.
But we really have a lot of obsolete code which have to be removed. But we cannot assert anything that piece should be removed because it really depends on the input. And we basically doing the parsing system. It heavily depends on the input. And to validate if this code is obsolete or not, we have to be sure that the external system will never produce those values, those combination of values. And that leads me to the conclusion that I never can be 100% sure that this piece of code is obsolete and can be safely removed. So I'm not hoping for the answer how to do that. I'm just trying to confirm my thoughts that my project cannot be safely refactored and the obsolete code in some way can be removed.
So it sounds like you're doing almost like, it's like language parsing or processing?
We parsing data. We are formatting it from one format into another.
Yeah. Yeah, and I can see in many situations like that, you may say, here's a condition I need to be able to produce or not produce. And to be able to go backward chain through all the possible inputs that could produce it is too complicated and impossible, right? I guess you're kind of saying like that. Anyway, I guess the main thing I'm going to say is that you may not be able to do this every place, you know, and that's fair, you know. It's like, I think in places where you're able to get pretty full coverage, you could choose to rewrite things in simpler ways, but you may not be able to remove certain things. And I didn't use that as an example, but there are definitely business cases where you can't get rid of certain things. I remember talking to a team once, and they were talking about, it's almost like annuities or some kind of like a thing like this, and they said, you know, we have all this very complicated code, but we can't get rid of this until 5 people in the world die, because it's essentially, by regulatory, this is something which has to be done for them periodically, and they can't actually remove this code until those clients are gone. And so yeah, there are always going to be cases where you can't do this kind of thing. But you know, I'd say look for the business cases where you can. And yes, about your particular situation, maybe I'd have to see more, but you know, your assumption is correct. There are cases where you can't. It's very fair. Okay.
Thanks.
Sure.
Thanks for the talk. I really like the idea that code is liability, not actually the asset. And I really like the idea that we have to explain the business, the technical depth, the notion of technical depth, and the problems we have in the system. And I do have a question related to that. How can I start explaining these things to business, being just a software engineer, when I have like layers of management on top of me, and all people tell me like, you don't know anything in this business, like you're just writing code. You cannot reason about it. We've been in the business for 10 years. What are you talking about, you know?
Well, the thing is, for anybody that you interface with as a technologist in an organization, the people you interface with who are not technologists, I'd say start here. Create a simplified view of what the system is. Grade the health in subjective terms for each of these pieces, and make sure you have a conversation continually about this. And the thing is, if you have that conversation over the course of a year, for instance, they start to see how their decisions impact the health grades you're telling them about. And then they start to go and get a sense that the code exists, right? That basically this is an impact of the things that they choose to do. So it's really about transparency, being transparent about the impact of feature selection on the code base. And so this is not going to be the entire organization in the beginning getting this, but the non-technologists that you do interface with will get a feeling for this. And then maybe they will be in a position to explain this to other people in the organization. It's like, well, yeah, I know we want these features, but it's like, yeah, I understand. When he says it's not a good idea right now, we know why. We know that there's, we know what happens when we do that, right? So it's really that kind of start. It's going and making, it's tough for us as engineers because we want to give all the detail, but making a simplified picture and over time getting people used to seeing what impacts are is a good start, okay?
Could you explain a little bit your approach with capturing the value of the method before you do splitting it into parts?
Splitting it into paths. Are you talking about like the thing where you take a variable and you sense it?
Yeah, public variable.
Yeah, well, I think...
I mean that you rely on some input and you need to check. So you take a copy of that method and split it into parts and then compare these two values for the same input? No?
So, well, what you do is typically you have, say, a big method and you put these variables in, you assign to them, but you write several test cases to go and see what happens to that variable under different inputs. And then when you've done that, then you can go and say, oh, now I can do a refactoring and see that those tests still pass. If they still pass, I have provided safety for my refactoring. And then I can remove the variables and remove those tests and check in the code.
Have you tried to use Scala check?
Yeah. Well, no, not Scala check. I've tried to use quick check in Haskell. I think, yeah, property-based testing tools are very powerful. I think we're going to see more of that use in the industry, but I think there's too much to say about that right now.
It's like an answer for the guy in the first row. So if he can use some random input. So guys, could you tell a little bit about property testing?
Briefly?
To the guys.
Yeah, sure. So with property testing, what happens is you look at your code and you try to determine certain things that will be true based upon your assumption of what it should be doing. And quite often these are mathematical, like idempotence and reflexivity and all these other things of inputs. And then you say, these are properties, and then there's a checker that goes and, based upon the properties, produces many, many randomized inputs and sees that those properties hold. And when those properties hold, then you have, an assurance that things are pretty good, but when they fail, you may have found a bug, right? So it's a very randomized testing strategy. And again, this is almost like the production coverage stuff we talked about a little bit earlier. It doesn't prove that there isn't a bug, but it can show you where there is a bug at times. The thing which is tough about property-based testing is to start to adopt the algebraic mindset of being able to formulate the properties. So like example, you may have a sort, that that it should be idempotent. If you sort the same thing twice, you should have the same outputs. You can check for that as a property. You can check to see that if you have random inputs and you put a value in the front of it or the same value in the back of it, when you sort, you get the same thing. It's a very good approach. You may be able to use this in the context of what you're doing, but I don't think it will give you a definitive answer about whether you can actually remove something or not based upon what you have. So, fair enough.
Thanks.
Any other thoughts, questions? Okay, well, thank you very much.